When humanity decided to build the James Webb Space Telescope, we were aiming for something audacious. We wanted to look back in time, not just a little bit, but all the way back to the universe's infancy, to a time just a few 100 million years after the Big Bang. Think of it as opening a cosmic photo album to the very first pages, where the first stars were just beginning to switch on and galaxies were starting to assemble from primordial gas. To do this, we built a magnificent golden eye, a set of segmented mirrors over 6 meters across, and sent it 1.5 million kilometers from Earth. From this distant cold outpost, JWST can capture the faint ancient light that has traveled across billions of light years to reach us, a journey that began when the universe was less than 1/10 of its current age. The telescope unfolded its mirrors in the deep dark of space, cooled its instruments to near absolute zero, and began to stare. It stared into patches of sky that looked utterly empty to our previous telescopes, seeking the whispers of creation. This is the heart of scientific exploration. You build a new tool not just to confirm what you already know, but to find the things you never even knew to ask about. Every time we have opened a new window on the cosmos, whether through radio waves, X-rays, or now infrared light, we have been met with surprises. The universe, it turns out, is always more clever and more creative than our imaginations. JWST's mission was to witness the cosmic dawn, the moment when the Dark Ages ended and the universe filled with light for the first time. What it found was beyond our wildest expectations. The very first images revealed a cosmos teeming with galaxies, far more numerous and more mature than our theories had predicted. It was like finding a photograph of a 1-year-old child who could already read and write. Our models of how quickly galaxies could form and grow were immediately thrown into question. But among these early galaxies, something else appeared. Sprinkled across the deep field images were hundreds of tiny, faint red smudges. They didn't look like the sprawling, majestic spirals we see today, or even the clumpy, chaotic galaxies of the early universe. They were just dots. Little red dots. These weren't just any dots, though. Their color told a story. The redness comes partly from something we call cosmological redshift, the stretching of light as the universe expands, which makes distant objects appear redder. But there was more to it. These objects were also intensely compact and surprisingly faint. They were a brand new cosmic mystery, a set of unexpected data points that didn't fit neatly into any of our existing boxes. And in science, a mystery is an invitation. It's a sign that we are on the verge of learning something profound, something that will force us to rethink our place in the cosmic story and the processes that built the world we see around us today. So what were these enigmatic little red dots? Astronomers around the world immediately got to work, pointing JWST back at them to gather more data. The first and most obvious guess was that they were simply very small, very distant galaxies. Perhaps we were seeing the tiniest building blocks of later, grander structures like our own Milky Way. This idea made some sense. After all, big things often start small. But as we looked closer, the theory began to fray at the edges. When we calculated their sizes based on their brightness and distance, we found they were ridiculously compact. Some were just a tiny fraction of the size of our galaxy, yet packed with stars, making them incredibly dense. So dense, in fact, that our models suggested they should have collapsed under their own gravity. Another leading hypothesis was that we were looking at quasars. A quasar is the brilliantly luminous core of a galaxy, powered by a supermassive black hole actively swallowing gas and dust. As material spirals into the black hole, it heats up and shines with unimaginable intensity, often outshining the entire galaxy it lives in. This could explain the compact nature of the dots. However, this idea also ran into trouble. Most of the red dots were simply too faint. Quasars are cosmic lighthouses, blazing across the universe, but these objects were more like cosmic candles. Furthermore, spectral analysis in early 2025 showed that the light from the dots had features of starlight, not just the signature of a violently feeding black hole. The mystery deepened. If they weren't typical galaxies and they weren't typical quasars, what were they? Scientists considered the possibility that they were heavily obscured by dust. Perhaps these were powerful quasars or bright young galaxies, but they were hidden behind a thick veil of cosmic dust, which would absorb their bright blue and ultraviolet light and re-radiate it as redder infrared light. This was a plausible explanation, one that could reconcile their faint red appearance with a powerful engine inside. But science demands evidence. Using JWST's other instruments and the ALMA telescope array, astronomers looked for the telltale heat signature of that dust. But in May 2025, they found none. The dust simply wasn't there. We were left with a genuine cosmic conundrum. We had a collection of objects in the early universe that were too compact to be normal galaxies and too faint to be normal quasars. And they weren't hiding behind dust. They were something else, something new. This is the best kind of problem to have in astrophysics. It means our understanding is incomplete, and there's a discovery waiting to be made. The universe was showing us a new class of object from its earliest moments, challenging us to expand our theories and imagine new possibilities for how the cosmos came to be. The little red dots were no longer just a curiosity. They were a direct challenge to our models of cosmic evolution. As old theories crumbled, new ideas rose to take their place. In a paper published in August 2025, a fascinating new explanation was proposed by researchers Avi Loeb and Fabio Pacucci. They suggested we look not just at the stars and gas, but at the invisible scaffold upon which galaxies are built, dark matter. We know that galaxies form inside vast, invisible clouds of dark matter called halos. The gravity of these halos pulls in ordinary matter, which then cools and collapses to form stars. The new theory hinges on a simple but powerful idea. The halos spin. Just as a spinning ball of pizza dough flattens and spreads out, a rapidly spinning dark matter halo will stretch the galaxy forming within it into a wide, flat disk like our Milky Way. But what if a halo wasn't spinning much at all? The researchers calculated that in the rarest of cases, the bottom 1% of halos with very low spin, something different would happen. Without that centrifugal force pushing everything outward, gravity would be overwhelmingly dominant. Gas and stars would be pulled into an incredibly tight, dense and compact ball. These slow-spinning halos would act as cosmic pressure cookers, forging small but intensely concentrated galaxies. According to this model, the little red dots aren't a strange new type of object, but rather a snapshot of a very specific and very early stage of galaxy formation, one that only happens in these rare, quiet corners of the universe before they have a chance to merge and spin up. At the same time, another compelling theory gained traction, one that puts black holes back at the center of the story, but in a clever new disguise. This idea proposes that the red dots are quasi-stars or black hole stars. Imagine a massive, growing black hole at the core, but instead of being a naked quasar, it is hidden inside a gigantic, puffy envelope of hot gas. This gaseous shell would act like a lampshade, absorbing the intense ultraviolet and X-ray radiation from the black hole and re-emitting it as cooler, redder light. This perfectly matches the observations: a compact engine, a reddish glow, and the absence of a classic quasar signature. It would represent a missing link in the growth of supermassive black holes. This has sparked a lively and healthy debate within the scientific community, which is exactly how science progresses. The truth might not be a single one-size-fits-all answer. It's entirely possible that the little red dots are a mixed bag of cosmic phenomena. Some of them could be those compact galaxies forming inside slow-spinning dark matter halos. Others could be these shrouded black holes or quasi-stars growing in secret during the universe's dawn. Data from JWST even shows that in some dots, gas is swirling at incredible speeds, a smoking gun signature of a black hole's presence. The challenge now is to sort them out and determine which explanation fits which dot. So why do these little red dots matter so much? They are far more than just faint smudges in a telescope image. They are clues from the scene of a cosmic event that happened over 13 billion years ago. Unlocking their secrets gives us a direct line into the physics that governed the universe in its formative years. If the slow-spinning halo theory is correct, these dots provide a powerful new way to study the nature of dark matter. By finding where these compact objects are clustered, we can map the weather of the cosmic web, identifying the quiet, low-spin regions and testing our fundamental theories about this mysterious substance that makes up most of the matter in the universe. On the other hand, if they are quasi-stars, they solve one of the biggest puzzles in modern cosmology. How did supermassive black holes get so big, so fast? We see enormous black holes, billions of times the mass of our Sun, in the very early universe. And we've struggled to explain how they could have grown to that size in such a short amount of time. The quasi-star phase could be the answer. A period of rapid hidden growth where a black hole could bulk up quickly before bursting forth onto the cosmic stage as a brilliant quasar. The little red dots would therefore be the baby pictures of the universe's biggest monsters, revealing a critical, previously unseen chapter in their life story. The debate is far from over, and that is what makes this field so exciting. Future observations with JWST with even longer exposure times will search for even more distant red dots. We can test the slow halo model's prediction that these objects should be found clustered together, far from the gravitational influence of larger galaxies. We can also hunt for similar objects closer to home, as some astronomers have already started doing, to study them in greater detail. Each new piece of data will help us either confirm one of these leading ideas, or perhaps point us toward a conclusion that is even more strange and wonderful than we can currently imagine. Ultimately, the discovery of the little red dots is transforming our view of the early universe. They are forcing us to refine our models of everything from dark matter dynamics to the birth of black holes and the assembly of galaxies. They remind us that the cosmos is a complex, interconnected system where dark matter, light matter, and gravity dance together in ways we are only just beginning to understand. These tiny, faint objects, barely visible at the edge of creation, are not breaking physics. Instead, they are enriching it, pushing the boundaries of our knowledge and fundamentally changing how we read the first, most important chapter in the story of our universe.